Hello folks, welcome to CS-412 Software Security. This is the speedrun of OXOD and we are going to talk about mobile ecosystem and the mobile ecosystem Android in particular. This is the second case study that we're going to discuss where we're going to focus on different kind of security environments and security extensions. The learning goals for today are as follows. First, we want to understand the differences between mobile and classic computing and model threats of mobile systems against different kind of attack vectors. We'll discuss security advantages and limitations of using a central marketplace to install applications, and for Android, argue how permissions work and how applications protect themselves against threats. So these are the learning goals for today and also what we're going to discuss today. So let's focus on mobile computing. This is a fairly recent endeavor, so it's only like 15 years old-ish, and is still massively changing from year to year. So you're still seeing advantages or advances on mobile computing on the security and privacy front moving forward, and it's still rapidly evolving. Now, mobile security is different from desktop systems, right? So a mobile system is very different. On one hand, it has access to much more personal data, including your photos, your fingerprints, but also sensors that could be violating your privacy, as in GPS, camera, microphone, and whatnot. Right? So in addition to that, these devices are connected to the internet and provide fast access to different kind of information. Today we're going to focus on mobile security in particular around the Android ecosystem. There's a whole class on mobile security that I highly recommend, and this is the MobiSec class by Yannick Fratantonio that you can find here. So if you're interested in this topic, I highly recommend actually going to that class and then exploring this in a bit more detail. Now, if you think about this, let's say 15 years ago, you're tasked to develop a mobile computing ecosystem. What kind of features do you need? How do you ensure that devices are secured? How do you protect the user data? And most importantly, as a company, how do you make money? Not necessarily just by selling the device in itself, but also in providing a whole ecosystem around it that allows you to continuously make money. Now, in the mobile ecosystem, the goal is to actually run mobile applications. These are slightly different from desktop applications, as in mobile applications are clearly geared towards a single task, whereas desktop systems, especially in a graphical user environment, tend to become more feature-fledged and have more different kind of functionalities. So diversity and usefulness of these mobile apps drive the customers towards certain applications and then allow them to spend money on it. The mobile ecosystem, to actually encourage developers, must give different kind of incentives to them. And there's trade-offs and strategies between these different ecosystems that exist. So Apple and Google have slightly different strategies, but for both of them, the apps remain crucial. Now, Apple had a first mover advantage, so they were a little bit faster to market. Even though both Apple and Google were developing the Android system at the same time, Apple managed to actually release their devices a little bit earlier, a couple of months before Google did. And this allowed them to translate this first mover advantage into a huge gain throughout the ecosystem and throughout the past decade or 1.5 decades. Apple's ecosystem is closed, right? So they do not release any kind of source code. They are in full control of the hardware platform, and they can actually command to the carriers and legacy providers on what they actually want to do. Android, on the other hand, is mostly open source. So Google's still playing some kind of catch up as part of the Open Phone Alliance and giving carriers kind of a much more freedom in designing, customizing their systems, but also to the vendors. So the Android ecosystem has a lot of different vendors that results in a lot of diversity between applications. So this gives you more of a choice as a customer, but also brings challenges, especially on the security side, which we will discuss in a bit. You may have heard of the Microsoft phones. They launched in 2010. So they were a couple of years late to the party, not too much, just like a couple of years. They had very nice phones, but had very few applications. This lack of applications then resulted in the downfall of Microsoft and made them disappear fairly soon because they couldn't reach critical mass of developers switching to their ecosystem. Application developers are somewhat okay, even though not super happy, about developing 2 apps. They would never develop 3 apps in a further segmented ecosystem. In today's class, we will focus on Android, but many of the observations also translate to iOS. Android is the most commonly used mobile ecosystem, has over 2 billion active users, or had 2 billion active users about 6 years ago. Now it's likely quite a bit more. And the diversity between different phones is much bigger on Android. So Android has super cheap devices for around 50 Swiss francs or 50 US dollars, up to super expensive high-end phones for over 1,000 Swiss francs or dollars. So in 2016, Android generated 31 billion in revenue, so which is quite a massive amount of money. There's 4,000 different devices and now even more. And sadly, Android Gingerbread had the highest crash rate overall. Now, Android evolves quite a bit. Each year there's a new Android version being released. And just a couple of weeks ago, we had Upside Down Cake, which was Android version number 14. The API version is not exactly clear at the time of this recording. Last year's version was Tiramisu, then before that Snowcon, Red Velvet Cake, Android Q, Pie, Oreo, Nougat, Marshmallow, Lollipop, and so on, and going back even further to 2005, when Google initially bought Android and the first SDK was released in 2007. Right? So Apple's iPhone and Google Android SDK were released at the same time, but the first devices, Apple devices, were available right away, while as Google was a couple of months late, where the devices were available in 2008. So being a bit late to the party had a huge disadvantage, but now the ecosystem is quite a bit bigger and more people will be using Android compared to iPhones. Now, each year there's a new Android release, and some of the phones receive updates to the latest release. And phones usually receive updates for 1 or 2 years after being sold, and then they no longer get any kind of security or system updates. If we look at the Android distribution from January this year, these are the latest numbers I could find in May this year. We see that the distribution is quite skewed. So there's a couple of very old devices that are 10 plus years old with KitKat, Lollipop, and so on. And the majority of the devices is between 2 and 4 years old. Now, if you want to support around 70 to 80% of devices that are out there, if you're developing an app, you need to take an API version that is around like 2 or 3 years back, right? So that's 2 or 3 years old. Now, this is an interesting challenge, right? Because each year a new Android operating system will be released, a new Android API version will be released, which will come with a certain amount of changes, new features, new opportunities, things that are easier. And when you're developing your app, you have to decide which API version you are targeting. And the later the API version, the more features you will get. But the higher the API version that you are using, the fewer devices you will actually have. So if you would be targeting Android 13 in January 2023, you would only be able to reach 5% of the devices, but you could use the latest set of features on that system and the latest APIs. So this is an interesting trade-off here between the amount of devices that could install your application and run your application versus what kind of features you will get. Android apps are developed in a mix between Java, Kotlin, and C and C++. The apps execute in the Android framework, which is an extension to the Java SDK, with access to sensors such as location, accelerometer, camera, whatnot, network and storage, and also the framework that provides this rich API and runtime system from the app to the outside. So for example, where the app can be asking for I/O, and from the outside to the app, where the app can provide services. And we'll talk about this a bit. Each app has a unique name. You can think of this as almost like a fully qualified domain name in a URL or a username. This package name has to be unique, and this unique identifier is used across the whole system. No two apps can share the same name on a device and in the Play Store. So this is globally unique in the Play Store, and on the device you cannot sideload or install applications that clash with other names because it's used as an internal identifier. Now, compared to regular applications, there is no main functions, or there's no clear function where the app starts executing. The user interaction happens through widgets. These are kind of screens, graphical screens. Both the app and the APIs that Android provides are event-driven. So as an app developer, you can register certain listeners to be informed when certain stuff happens. And then a callback will fire whenever an event is being dispatched. The apps then consist of different components. Activities, which describe user interfaces, services, which do the actual work, broadcast receivers, which react to system events, and content providers, which provide data storage. Let's quickly discuss these individual items in a bit more detail. Each activity defines a screen and like a way to interact with the application. Think of this as a UI form, right? There can be many activities per app, but the developer has to define one main activity. External applications may start specific activities if that is allowed, right? So the application could be exporting certain activities, and other applications can call these different activities think of this as sub-functionalities or different functionalities that can be reached directly. At least the main activity must be public, and this main activity is being launched when you, under quote, start the app. All the other activities can be used either by other apps, internal apps, to launch specific functionality directly. The next component is a service. This performs actions in the background. For example, Spotify has a service that in the background keeps downloading the next music, the next song as a file, and will then play it continuously while the app is running, allowing you to have other applications in the foreground. So this background service will make sure that the next song is being downloaded and played while you can do other things with the phone. Services do not provide a user interface, but activities can change the global state and interact with services to set up whatever needs to be done. A broadcast receiver is the next component, responds to different kind of system events. System serves events to apps even if they are not currently active. And for example, a message received, battery is charging, Wi-Fi is connected. The broadcast receiver will then launch the necessary reaction to it and fire the events to make sure that this is correctly handled. Right? And as an application, you could register for certain events, which would then be signaled whenever this happens. Content provider, this is a simple way to manage stored data. For example, SQLite would be a content provider which provides an API for data access, also allowing external access, allowing you to potentially share the data from your app with other apps as well. Let's go through an example of using the Android location API. Here you define a My Location listener where we just instantiate the listener, and you request location updates every 5 seconds from the GPS provider if your change is more than like your position changes more than 10, right? Fair enough. In the location listener, you react whenever the location changes, and you will display an overlay that says, hey, the location has changed, and this is the current latitude and longitude. Fair enough. Another example would be I/O. You have an output stream writer where you write to a scratch directory of your app. You write the data, you close it. Android will then go down the stack, starting from the Java side to the libc to system calls, continuously checking if you have the right permissions and allowing you to do so. So this will map to system calls open, write, and close. The Android stack is rather complex, so it consists of several layers and changes throughout, changing different aspects throughout these different layers. So there are changes to the Linux kernel, the hardware abstraction layers, the available libraries, the Java API framework, and the different kind of system apps. So let's dive into the bottom half for a second. Right, so Android uses the Linux kernel, which is a common kernel, but changes it in a couple of interesting ways. So it will come as a different kind of power management that's a bit more aggressive, and Google's implementation of IPC, namely the binder API, which allows applications to communicate with each other through messages as supported by the Linux kernel. The hardware abstraction layer provides a unified interface for audio, Bluetooth, camera, and sensors, and so on, which then maps to individual drivers in the Linux kernel, which can then be hardware specific, right? So the Linux drivers will be hardware specific, whereas the hardware abstraction layer will be generic, exposing a generic API to the different applications on the upper half. The top half looks a bit as follows. There's the Android runtime, art, and the different kind of core libraries that is installed, in addition to native libraries that are provided by the system. For example, a WebKit browser, OpenMax, libc, OpenGL for GPU interactions, and different kind of media frameworks. On top of that is the Java API framework for different with managers for activities and whatnot, content providers, the general system definition and whatnot, and then system apps that are installed on top of it, depending on whatever your manufacturer installs or feels the need to customize or adjust. If you look at the security goals, Android aims at specific security goals throughout the runtime of the system. Isolating individual applications, making sure that they can only communicate through the binder API, through interprocedure calls, protecting system resources from applications, then vetting applications online, and protecting data of the user or the users that are on the system. Interesting to note is that Android until version 5 was single user, so only a single user could be working on a given phone or tablet or whatnot. Since Android 5, multiple users are allowed. Now, Android is built on Linux, and each app gets assigned its own user ID. Right, so this is interesting, right? Each application has a unique user ID. So each application is a user. And each package is a simple user, is installed as its own user. Each app runs its own sandbox with a restricted file system, process isolation towards other systems, and a very limited chain of system calls that are allowed. Interactions between apps are restricted through the API and the binder IPC. Each app has an associated policy which encodes the permissions that is allowed to be given. Right? Think of it as an app will only be able to access the camera API if it is allowed access to it. Apps are signed by the developer using a public key, vetted and then installed from a central market. Apps are carefully vetted server-side, and only approved apps can be installed from this market. So this is a single kind of source of applications for the majority of users. And this allows Google to actually verify the security properties of given applications and figure out if something can go wrong. In addition, it gives Google a massive amount of control over what kind of applications can actually be installed and to make money out of the platform. So this was the key advantage of making money when moving to the mobile ecosystem compared to the previous software system. Previously, anybody could offer software through their own kind of market, or through their website or whatnot, right? Providing an ad hoc market if needed. On mobile platforms, this was changed through, replaced through a central market that either Apple or Google controls. The applications run in a Java-like sandbox, restricted to these user-granted permissions, and then leverage this well-defined API channel to communicate with other apps. The system is hardened against local users and different kind of app-based attacks. The Android leverages the Linux kernel as a foundation, and using this has a couple of advantages, right? So Google could have created their own kernel or microkernel, but leveraging leveraging Linux in Android gives them process isolation, user-based permission models, RBAC extensions, secure IPC, and so on right away. Also, they trim down the kernel as much as possible, removing any kind of components that are not strictly necessary. And then the kernel also provides effective resource isolation for hardware accesses. The drivers are readily available because Linux has a long history on ARM. Now, the isolation that Android implements requires that each application runs as its unique user. There are stringent permissions on file systems where each user only has access to the few files that belong to the application. The hardened Linux kernel protects the applications, and SE Linux applies control policies on the processes to make sure that an application cannot escape its sandbox. Android also follows the idea of safe defaults. So it uses verified boot and file system encryption. The root partition is mounted read-only, so even if there is an exploit, you will not get write access to the root partition. So you will not get persistence across reboots. The crypto API provides safe implementations and key management. And in user space, we've got stack canaries, integer overflow mitigation, double free protection, fortify source, non-executable bits, ASLR, Pi, RelRo, and so on. In each release, there's going to be more security updates, patches, toolchain updates, and tighter security defaults. And another interesting observation is that Android or Google is moving more and more of the user data, such as private keys, fingerprints, and whatnot, into the trusted execution environment to make sure it is protected even against a full system compromise on this end. Applications, each app runs in a private folder. You can start other apps from your app. So the main activity is always exported. So one app can easily start another app with a couple of parameters. The app can show things on the screen if it is in the foreground, and everything else requires a permission. Now think about how would you restrict apps from these attacks, and what attack vectors will remain. Android leverages a complex permission systems on this per app basis, as you likely knew, and splits permissions into several categories: normal, signature, and dangerous. Normal permissions are considered no risk and just allowed by default if the application declares them. Signature permissions are granted if the app is signed with the same key as providing the service. So this allows a set of apps to communicate with each other. And dangerous permissions require explicit permission or acknowledgement through a pop-up. Default permissions are as follows. So there's a couple of things like audio settings, Bluetooth access and whatnot, but also NFC, transmit IR, and whatnot that could potentially be dangerous and could require some additional vetting. But those have been considered safe for for most use cases, and most applications use them in a reasonable manner. Now there's a bunch of dangerous permissions, such as accessing your calendar and private information, looking at your call logs, making outgoing calls, camera access, contact access, location access, microphone access, phone status, sensors, text messages, or storage. These are considered privacy sensitive or otherwise sensitive and require explicit acknowledgement by the user, as not every app should have access to all the data. Now this is a fundamental difference to a desktop system. Right? On a desktop system, if you're running an application as a user, it just has access to all the data in your home directory, which will be a massive amount of data, right? And there's no distinction between individual apps. Each app on a desktop system has the same access, while as on Android, the access to files or to the system state is segregated by the application and requires explicit acknowledgement. Now, different Android versions have different approaches for dangerous permissions. For recent Android versions, the application will ask at runtime, right? There's going to be a pop-up. Do you want that the application gets access to the microphone only this time while using the app, or forever? And then you can actually choose and assess the context in which the application is using this, this privilege. For earlier Android versions, the Android simply asked at installation time, and then it is used for forever. The runtime prompt allows the app to run without writes ahead of time and gives the user context where the write is used. The runtime prompts allow the user to decide on a case-by-case basis. But then this may also be more annoying because you get more and more pop-ups, and users could be trained to just click yes all the time. So this is an interesting trade-off between user fatigue and the flexibility to custom tailor this on a case-by-case basis. Android also has some missing permissions, for example, accessing any kind of sensor such as temperature, accelerometer, gyroscope does not require any kind of permission. The security solution here is to simply disable sensors if the app is not running in the foreground. This can work, but is also a kind of a limitation where the app wouldn't know if the sensor is working or not. Android intents, this is how Android implements IPC and communication between applications. So an intent is a simple message object that represents an intention to do something. For example, if your application wants to display a web page, it expresses its intent to view the URL by creating an intent instance and handing it off to the system. The system locates some other piece of code, in this case the browser, that knows how to handle that intent and runs it. Intents can also be used to broadcast interesting events such as a notification system-wide. Right? And one of the key additions to the Android system is the binder interface, which implements this IPC functionality. It enables an app to talk to other apps and is a core extension over Linux. It enables remote procedure call and IPC on the Android ecosystem. The proxy and the stub are auto-generated, and the binder call maps to an ioctl. That is an extension in the Linux kernel. So the app runs as a non-privileged process. If it calls location manager get last location, as we've seen in the example before, there's a binder proxy where it goes to the Linux kernel, binder driver, then to the stub on the other hand, the privileged process service that keeps track of the location, which then returns the data back to the app that had the permission. So it allows accessing sensitive data at an overhead of a couple of process switches, where it delegates the privileged information to this service on the other end. Applications are signed by the developer with their private key. but the certificates are not signed by any kind of global authority. So what do these certificates actually enable? Right? What do they not enable? Well, there's a couple of advantages for Google, but also for authors. It allows authors to be distinguished but not identified. So you cannot pinpoint a single author, but you can distinguish different kinds of authors. And also it allows you to distinguish normal applications and system applications if you pin certain certificates of system apps. You can detect the two apps are from the same author, such as Facebook and Messenger, and allowing it to share information as well. So for example, Facebook and Messenger can exchange information privately without other apps, without letting to know other apps. In the real world, Android apps share user ID. So apps from the same developer may share a user ID. So there's no separation between apps. The advantage is that they can share data on the system level without having to go through the heavyweight IPC process, right? So these apps could be sharing data through IPC, but with a shared user ID, they can share information through the file system or whatnot, and thereby speed things up quite a bit. Let's talk about some attack vectors on the Android ecosystem. So there's intents, unauthorized intent receipt, where the attacker creates an intent filter and receives the intents of other applications that contain privileged information. For example, an intent filter for web service intercepts, an online payment process that an app is trying to make, intent spoofing, where the attacker sends malicious intent to an intent processor, for example, flooding the network with malicious messages. And there's ongoing work to defend against such attacks, for example, by restricting communication among signed or trusted components. So you could make sure that you're only interacting with a trusted browser or whatnot. Another attack vector is communication. So there's insecure internet communication, Wireshark intercepting traffic, but also that Bluetooth, NFC, and IR infrared is not restricted. So the peripherals are not protected against malicious apps, as any app may access any paired device. So after you have paired your Bluetooth headphones, any other app, even a malicious app, could be interacting with the communication channel on your headphones and potentially compromise those as a lateral vector. This is an issue of the granularity of the privileges. So there's only one Bluetooth privilege. Therefore, privileges are per app and not per connected device. If you give an app the Bluetooth privilege, it can connect to all the Bluetooth devices that you have connected, not just the one that you wanted to use with. So for example, if you have a smart watch, the companion app will require the Bluetooth privilege, which then allows it to also connect to the smart speaker, even if the companion app should only communicate with your smartwatch. Another attack vector is over-privileges or over-privileged apps, which would allow confused deputy attacks, allowing an attacker to leverage bugs in another application to gain privileges. An ongoing issue also is the lack of device updates or updates in general, and it's a core problem with Android. There's a massive amount of fragmentation and heterogeneity. So devices, the software on devices is not updated. The vendors are only interested in selling you the device, not keeping you updated and not patching the vulnerabilities. Vendors are interested in customizing and branding, so they want that their device is being customized, which also prohibits Google from sending you updates. A solution that Google is trying more and more is to bundle some of the security updates with the Play services. So you may have noticed that the Play services are this massive kind of binary blob that keeps being pushed by Google every now and then. This is where they patch some of the most notorious and difficult vulnerabilities as an after effect. So this gives Google a little bit of power to patch certain issues, but it's a very limited solution, as it takes away control from the device vendors and also limits the amount of introspection you can do on the device, because this Play services blob is heavily obfuscated and very limited and cannot really be analyzed by developer or an analyst. Some historic attack vectors are insecure storage. So before that, there was no access, in earlier Android versions, there were no access restrictions on the SD card, and an attacker could read and write any kind of the data on the SD card. This was fixed in Android 5 when multi-user was also rolled out. The reason was that this provided a way to remap and remount the SD card for sharing data with a desktop, for example. So if you plugged the Android device into your computer and connected it through USB, the default implementation until Android 5 allowed or just remounted the SD card from the Android device to the desktop. And starting in Android 5, there was an overlay system developed that allowed it to securely share and map data between the desktop and the Android device. Now, the central market is a core security strategy. Developers must sign their applications, thereby become identifiable, which increases their switching cost, especially when they are at the whim of Google and the reputation engine that actually recommends their app to others. Because there's so many apps out there, it's going to be very hard for developers to be noticed, and they have to build up a reputation. This reputation can be leveraged by Google to decide which apps to check and vet carefully. So applications can be vetted based on these developer profiles. For example, you will be vetting an app carefully if the developer is not as well known and not as public versus like you can apply different kind of checks compared to others, right? So if you have a developer like that is very well known, you may apply other kind of checks that are less stringent because you're trusting that developer. So you can kind of shift the amount of resources that you need and only require the heavyweight dynamic analysis checks for applications or for applications that are from less known developers or potentially dangerous. Telemetry also allows Google to then tie malicious apps to different kind of companies and developers, and thereby kind of correlate and revoke applications across devices as well. So, quick summary. The Android security system or Android security evolved over time. Android itself is hardened against exploits. Developers sign applications, which identifies them, which comes at interesting trade-offs between the flexibility and the power of the checks. And applications are vetted centrally and then installed from this market, which gives Google a lot of power and control over the software distribution. This was all for this case study. I hope you enjoyed it. Thank you for your attention, and I'll see you around.